In this lesson, we're going to cover graphs of rational functions, and we're going to look at vertical, horizontal, and slant asymptotes, their x and y intercepts, holes, and end behavior. So here's our rational function. It's going to be anything of the form where we have a polynomial divided by a polynomial. The domain of the rational function is the set of all real numbers except the x values that make the denominator equal to 0. So with these problems, we'll have a rational function, and then we'll look at the polynomials in top and bottom, and if they factor, then we can cancel any of the common factors. But then, when we take the resulting fraction, if a is a 0 of the denominator, then we say that x equals a is going to be the vertical asymptote of the graph. Our next definition is a hole. In order to be a hole, it's going to be a point on the graph where the value of the function is not defined. So if the numerator and the denominator of the function have a common factor, let's say it's x minus a, if that factor cancels, then we say that x equals a is where the hole occurs. And then to find the corresponding y value of the hole, we're going to plug the x value into the reduced function. Next we have horizontal asymptotes. So again, if we have our reduced fraction where the top and the bottom polynomials have no common factors, the numerator's degree, we'll call it p, and then we'll say a is its leading coefficient. For the denominator, the degree is q, and its leading coefficient is b. We compare p and q. If p is less than q, then the horizontal asymptote is the line y equals 0. If p equals q, then the horizontal asymptote is the line y equals a over b, where again a and b are the leading coefficients of the numerator and the denominator. If p is greater than q, then the graph has no horizontal asymptote, but I have an asterisk here because if p is exactly 1 more than q, the rational function has what we call a slant asymptote. And then to find the slant asymptote, you divide p by q using long division, and then you disregard the remainder. But we'll go over examples so this will make a little more sense. This example says identify the vertical asymptotes, the horizontal asymptotes, and the holes for the following functions. So part A, we have f of x equals, and you can see the rational function. First step, we're going to factor the top and bottom. So we're going to factor the numerator and the denominator using t-charts. So this first polynomial becomes 2x plus 3 times the quantity x plus 2. And the denominator factors to x plus 2 times x plus 3. The common factor in the numerator and denominator is x plus 2, so those cancel. So our resulting function is f of x equals 2x plus 3 over x plus 3. And this is going to be the function that we work with when we identify these values. To find a hole, what you do is you look at the factor that was canceled, and the factor is x plus 2, so that means the hole occurs at x equals negative 2. Once you identify the x value, you take this negative 2 and you plug it in right here and here for x. So in the numerator you get negative 4 plus 3, and the denominator we get positive 1, so this becomes negative 1. And so the point we get for the hole is going to be negative 2 comma negative 1. Next, to find the vertical asymptote, again we're going to look back at this reduced fraction. So again we're focusing on this function right here, and you just look at the denominator and then ask yourself what makes the denominator equal to 0, and that would be negative 3. So x equals negative 3 is going to be our vertical asymptote. For the horizontal asymptote, we need to identify p and q. P is the degree of the numerator, so p is 1. Q is the degree of the denominator, so again you look at the highest power, which is x, and you ask yourself what's the exponent, so that's how you're getting q equals 1. And then you compare the two numbers with either a less than, an equals, or a greater than symbol. So I'm just going to put an equals right there so we know that p is equal to q. And let's scroll up to this chart right here. When p equals q, the horizontal asymptote is the line y equals a over b. A is the leading coefficient of the numerator, and b is the leading coefficient of the denominator. So our horizontal asymptote is going to be y equals, the leading coefficient of the numerator is positive 2, and the leading coefficient of the denominator, you look at this variable right here, and its coefficient is technically positive 1. So 2 over 1 is 2. So our horizontal asymptote is y equals 2. Here's our next example. We have f of x equals x plus 5 over x squared minus 25. The first step is to factor. And now we're going to check for common factors. You guys can see that x plus 5 is the common factor, so that cancels. So here's our reduced function. We get f of x equals 1 over x minus 5. Because we had x plus 5 and x plus 5 cancel, that means the hole occurs at x equals negative 5. Once you identify the x value of the hole, you take it and plug it into the function. So we end up getting 1 over negative 10, or negative 1/10. So our hole is the coordinate point negative 5 comma negative 1/10. To find the vertical asymptote, we're going to look at the reduced fraction right here, and you look to see what makes the denominator equal to 0, and that would be positive 5. So we get x equals 5 for the vertical asymptote. And then for the horizontal asymptote, we're going to set up our PQ chart. P is the degree of the numerator. Because you only have a constant and you don't have a variable, technically it's like x to the 0. So P is 0. In the denominator, your degree, you look at the x and its exponent is 1. And then you compare these values because 0 is less than 1. We write P is less than Q. So I'm going to look back at this table. When P is less than Q, the horizontal asymptote is the line y equals 0. All right, so I have everything filled in right here. For part C, we have f of x equals x over x squared minus 25. I'm going to take the denominator and factor it. So we have f of x equals x over the quantity x plus 5 times the quantity x minus 5. And then you notice in this problem, we don't have any common factors on top and bottom to cancel. So that means there's no hole in this graph. The vertical asymptote, you look at the fraction in reduced form, which is just itself, and then you look to the denominator to check what would make the denominator equal to 0. So this one would make x equals negative 5, and then this factor means that x equals positive 5. So we have two answers, and I just wrote it in the form x equals plus or minus 5. For the horizontal asymptotes, we're going to identify P and Q. P is the degree of the numerator, so you just look at the highest exponent, which is just 1. Q is the degree of the denominator, so I'm going to look over here, and the highest exponent is 2. So that means Q is 2. And then we compare the values with either a less than, an equal to, or a greater than symbol. So since 1 is less than 2, I wrote P less than Q. And again, I'm going to go back to the chart, and since P is less than Q, the horizontal asymptote is the line y equals 0. All right, so we have everything filled out right here. This example says graph the function, and we have x squared minus 9 over x plus 3. So the first step, we're going to factor the top. So x squared minus 9 factors to x plus 3 times x minus 3, and then I just left the denominator as x plus 3. And you guys can see that the common factor is x plus 3 and x plus 3, so those cancel. And then I wrote the reduced function as f of x equals x minus 3, so whatever expression is left. Okay, so this graph is a straight line, and because a common factor canceled, there's going to be a hole. And again, to find the hole, you look at the factor that was canceled. If you set that factor equal to 0, that tells you the x coordinate of the hole. So because the factor is x plus 3, that means the hole is at x equals negative 3. If you had a problem where the factor that canceled was x minus 3, that would make the hole at x equals positive 3. So again, if you take the factor that cancels and set equal to 0 and solve, that will give you the x value of the hole. And then we'll take this value, plug it in, and you get negative 3 minus 3. So the y value is negative 6, and that means the hole is going to be at negative 3, negative 6. All right, I'm going to go back to this function, and we're going to graph it. It's a straight line. The y-intercept is negative 3, so I just put a dot on the y-axis. And the slope is 1, so we're going to go up 1, right 1. So here's our line for f of x, but then again, we have a hole at x equals negative 3. So here's our graph. We have the straight line, f of x equals x minus 3, and then you can see right here at x equals negative 3, there's a hole. This example says find the slant asymptote of the function f of x equals negative 3x squared plus 2 all over x minus 1. So just to recap on why there's a slant asymptote, p is the degree of the numerator, so p equals 2. Q is the degree of the denominator, so q is equal to power of 1. And when we compare these, you have 2 is greater than 1, so p is greater than q. And if we look at our table over here, when p is greater than q, there's no horizontal asymptote, but again, there's a little note here that if p is exactly 1 more than q, that means the graph has a slant asymptote. So since p is exactly 1 more than q, it does mean that this graph has a slant asymptote. And to find the slant asymptote, we're going to do long division. Okay, so I have it set up. We're going to say what times x makes this first term. So we get negative 3x. Then we distribute that to both of these terms, and we write it down here. So let's double check this. We have negative 3x times x is negative 3x squared. and negative 3x times negative 1 is positive 3x. Now we add their opposites. So the first terms when we add down are going to cancel. And then here, think of this as just 0 plus a negative 3x. So that makes negative 3x. And then we're going to drop down this plus 2. And now we're going to start the process again. We're going to say what times x makes this first term. So negative 3. When we take the negative 3 and distribute it to both of these terms, we write it down here. Then add their opposites. The first term cancels out, and then we have 2 minus 3, which makes negative 1. So this is the answer, and that's the remainder, but you're supposed to disregard the remainder. So the slant asymptote is y equals negative 3x minus 3. Here's some tips when we finally graph an actual rational function. It says to consider the rational function where p and q have no common factors. So step 1, what we're going to do is we're going to take the original problem, factor the numerator and denominator, and then cancel any common factors. If no factors cancel, then the function has no wholes. If you have any factors that do cancel, then to find the whole, you just use, if it's x minus a, then the whole is going to occur at x equals a. And then you take that value, plug it into the reduced expression, and that will give you the points for the whole. Step 3, you're going to find any vertical asymptotes. So you take that reduced expression and you set the denominator equal to 0. To find x-intercepts, that's where y is equal to 0, so you set the rational function equal to 0. And when you cross multiply, you end up getting the numerator equals 0, and then you solve that. To find the y-intercept, you plug in 0 for x. And then horizontal asymptotes, you identify p and q and then use the chart. And then finally, we'll plot points if we're missing any parts of the graph. This example says graph the rational function using the provided steps, and we have f of x equals 1 over x minus 3. So step 1, nothing factors, so I just rewrote the function. Since there were no factors to cancel, then there's no wholes. To find the vertical asymptote, you set the denominator equal to 0. So for the vertical asymptote, we get x equals 3. To find the x-intercept, we set the numerator equal to 0. Since the numerator doesn't have any variables in it, we can't solve this, and in fact this is a false statement. And when you get a false statement, then there's no x-intercepts. To find the y-intercept, we plug in 0 for x, so you end up getting the fraction negative 1/3. So our y-intercept is 0, negative 1/3. To find the horizontal asymptotes, we're going to identify p and q. P is the degree of the numerator because it's just a constant, the degree is 0. Q is the degree of the denominator, so you look at the x and its exponent is 1. So q is 1, and then we compare these values. So p is less than q, and so you can go ahead and check the PQ chart, but when p is less than q, the horizontal asymptote is the line y equals 0. Now that we have all our information, let's go ahead and start filling out the graph. So we'll start with the vertical asymptote. We're going to draw a vertical line at x equals positive 3. So I put that right there. And then our horizontal asymptote is y equals 0. So it's kind of hard to see it, but I drew a dotted line right here on the x-axis. If we had any x-intercepts, I would plot those next, but we don't. So let's go ahead and plot the y-intercept, 0, negative 1/3. So the y-intercept, negative 1/3, I just put a dot right here. And you want to think about these graphs kind of divided by the vertical asymptotes. So because there's only one vertical asymptote in this problem, we're going to think of it as the left side and the right side of the vertical asymptote. So on the left side, we have this dot. And what we're going to do is we're going to draw the graph so that it kind of coasts along the asymptotes. So to the left, from this point, the graph just coasts along the horizontal asymptote. And to the right, it's going to kind of coast down along the vertical asymptote. So to finish our graph, all we need is 1 point on the right side of the vertical asymptote. So I just ask myself, what's a nice x value that's to the right of the vertical asymptote that we can plug into the function? So I'm looking and I'm thinking, let's go ahead and plug in x equals 4. So I plugged in 4 for x, and you get 1 over 1. So when x is 4, y is 1. So here's our point. And again, from here, we're just going to coast along the asymptote that's vertical and then coast along the horizontal asymptote. And there's our completed graph. Part B, we have f of x equals 2x squared over x squared minus 4. So the first step, we're going to factor. And there's no common factors on top and bottom, so nothing cancels. Therefore, we don't have any wholes. To find the vertical asymptote, you think about what would make the denominator equal to 0. So that's going to be negative 2 and positive 2. So I wrote that as x equals plus or minus 2. To find the x-intercept, what you're doing is you're plugging 0 for y. But if you set this fraction equal to 0, And if you were to cross multiply, you end up getting that the top is just equal to 0. So you don't really have to show all that work. You can just set the numerator equal to 0 and then solve. So we're going to divide both sides by 2 and then square root, just get x equals 0. So we got that x equals 0 and y equals 0. Anytime you get an x-intercept that's 0, 0, the y-intercept will be the same. Or if you wanted to solve for the y-intercept, you're just plugging in 0 for x, but if you plug in 0 right here, you get 0 on top. When you plug in 0 right here, you get -4, but 0 divided by -4 is just 0. To find the horizontal asymptote, we're going to identify p and q. P is the degree of the numerator, so we look up here and the highest exponent is 2. Q is the degree of the denominator. I'm going to look over here. The degree is the highest exponent, so it's also 2. And then we compare this, and 2 is equal to itself. When p is equal to q, the horizontal asymptote is the ratio of the leading coefficients. So in the numerator, you look at the highest exponent, and the coefficient is +2. And then we do the same thing in the denominator. You find the highest exponent, and its leading coefficient right here is +1. So our horizontal asymptote is the line y equals 2. Now that we have our chart filled out, let's go ahead and start drawing some of the stuff on the graph. So we have a vertical asymptote at 2 and -2. Our x-intercept and y-intercept 0, 0. So I put the point right there. And then we have a horizontal asymptote at y equals 2. At this point, we don't know for sure what the graph is going to do from this point. It could kind of curve down like this and look kind of like a mini parabola inside here. It could curve up to the right, or it could start up here and curve down. So we have to plug in some points. So you want to think of your graph in parts according to these vertical asymptotes. So first, I want to look to the left of this vertical asymptote. So if we go over here, we could plug in -3 or -4. I'm just going to use -3. So you're going to plug in -3 for the x's. In the numerator, we get 9 times 2. In the denominator, we get 9 minus 4. And because we're going to plot this value, let's go ahead and change this to a mixed number. So 5 goes into 18 3 times with 3 left over. So because we have our point right here, we can draw the graph. It's going to coast along the asymptote and then go to the left along that horizontal asymptote. Inside here, again, to figure out what the graph is doing, we're going to plug in -1 and +1. So the point is -1, -2/3. And I put the point right there. Let's do the same thing by plugging in +1, and you end up getting the same y value. So you have -2/3 again. So we can see that the graph is going to go down to the left and down to the right. Okay, and then we just have one more section that would be to the right of this vertical asymptote. So let's plug in +3. And you're probably noticing that because these are both x squared, you're going to get the same exact value as you did when you plugged in -3. So when you have x equals 3, your y value is 3 3/5. And let's go ahead and draw this part of the graph like this. So here's your final graph. This example says x minus 5 over x squared minus 25. So our first step, we're going to factor. And we do have a common factor of x minus 5. So I'm going to write the reduced function over here. So we have f of x equals 1 over x plus 5. Since we had a common factor that cancels, that means this graph will have a hole. The common factor is x minus 5, so that means the hole is going to occur at x equals +5. And then we take x equals 5 and we'll plug it into the reduced function. When you plug in 5, you get 1/10. So the hole occurs at 5, 1/10. To find the vertical asymptote, you look at the reduced function and you set the denominator equal to 0. So we get x equals -5. To find the x-intercept, we set the numerator equal to 0. But again, since there's no variable in the numerator, you just have this statement which is false. So that means there's no x-intercepts. To find the y-intercept, we're going to plug in 0 for x. So we end up getting 1/5. So our y-intercept is the point 0, 1/5. To find our horizontal asymptote, we're going to look at p and q. P is the degree of the numerator, so since it's a constant, p is equal to 0. Q is the degree of the denominator, so we get q equals 1. And then we compare the values, so we get p is less than q. When p is less than q, according to the PQ chart, that means the horizontal asymptote is the line y equals 0. Now that we have everything filled out, let's go ahead and start graphing. So I drew the vertical asymptote at x equals -5. The horizontal asymptote is a line y equals 0. I'm going to plot the y-intercept next, so 0, 1/5. So that point's right here. And again, to finish off the graph, we have couple things happening here. You have your vertical asymptote, so since we already have a point to the right of it, we can go ahead and fill in that part of the graph. So from this point, you're just going to coast along the asymptote to the right, and then to the left, you're just going to coast along the vertical asymptote up. Next, we're going to look at where the hole is. The hole is at the point 5, 1/10. So right here, when x equals 5, I drew a hole. And then finally, we just need a point on the left side of the vertical asymptote. So let's go ahead and plug in -6. So plugging in -6 to the reduced function, we have 1 over -6 plus 5. So you end up getting -1. So here's the point -6, -1. And then draw your graph so it coasts along the asymptotes. All right, so here's our final graph. Our last example says f of x equals x cubed minus 1 over x squared minus 9. So our first step, we're going to factor. The denominator is a difference of squares, so that factor is x plus 3, x minus 3. The numerator is a difference of cubes, so that factors a small parentheses and a big one. Then you ask yourself what cubed makes x cubed and what cubed makes 1. So you get x and 1. Right here you do x squared. Next you multiply these two, so x times 1 is just x. And then right here you square 1, so you end up just getting 1. And then you use the acronym SOAP. So it's going to be same, opposite, always positive. So the same is negative, opposite is a plus, and then always positive. And you can see in factored form, nothing cancels. Okay, so I just wrote that in right here. Next, because nothing canceled, there's no holes. To find the vertical asymptote, set the denominator equal to 0, so you get x equals plus or minus 3. To find the x-intercept, you set the numerator equal to 0. So setting this up, you can see right here, this is going to produce the value x equals positive 1. And because this was factored using a difference of cubes factor pattern, this part of the problem will not produce a real number. So our only answer is going to be x equals 1. So our x-intercept is 1, 0. To find the y-intercept, we're going to plug in 0 for x. I'm going to use the original function to do so. So you end up getting -1 on top and -9 in the denominator. So that makes positive 1/9. So our y-intercept is 0, 1/9. And to find the horizontal asymptotes, we're going to look at p and q. P is the degree of the numerator, so we get 3. Q is the degree of the denominator, so you get 2. Since p is greater than q, that means there's no horizontal asymptote. So then we check if p is 1 more than q, which it is, so that means there is a slant asymptote. So let's go ahead and find it using long division. So we're going to take the numerator and divide by the denominator. Okay, I got it set up, so we ask ourselves what times x squared makes this first term, so we get x. Then take this x and distribute to all these terms and put it down here. Now we're going to add their opposites. The first terms cancel. Next you just have 0x squared, and then this makes positive 9x, and drop down the -1, and that's going to be the remainder. So the slant asymptote is just y equals the answer, disregarding the remainder, so you get y equals x. Okay, let's start putting this on the graph. We have vertical asymptotes at 3 and -3. Then we have the slant asymptote is the line y equals x. So the y-intercept is at 0, and then the slope is 1, so we're going to go up 1, right 1. And then we can plot the x and the y-intercepts. So we have the point 1, 0. Then we also have 0, 1/9. So that point's right here. And at this point, to finish the graph, we're going to plug in some x values. So it looks like we're going from this point to this one, and then if I had to guess, we would coast down along this vertical asymptote. But just to be sure what's happening to the left, I want to plug in -1. Since nothing canceled when we factored, we can use the original if that's easier to plug in. So -1 cubed is -1, and then -1 squared is positive 1. So you get -2 over -8, which reduces to 1/4. So at -1, we're going to go up 1/4. So since this point was 1/9 and then this is 1/4, you can tell that the graph is going to keep coasting up towards that vertical asymptote. And then we can say that from here it goes to this point and coasts down. So it's kind of strange that the graph crossed the slant asymptote, but that means out here and here the graph will probably abide by this slant asymptote. So next, let's plug in -4 to find out what the graph is doing to the left of this vertical asymptote. So right here we get -64 minus 1 is going to be -65. And here we get 16 minus 9. And we'll rewrite this as a mixed number. When x is -4, we get -9 and 2/7. So -4, and then we go -9 and 2/7. So -1, -2, 3, 4, 5, 6, 7, 8, 9. It's going off the graph, so it's about here. Okay, so the point is here. And we're going to come up and then coast along the slant asymptote. So that gave us the graph to the left of this vertical asymptote. And now let's go ahead and plug in positive 4. So we get 64 minus 1 is 63, and 16 minus 9 is 7. So when x is 4, we get positive 9. So I'm going to go right here and then count up 1, 2, 3, 4, 5, 6, 7, 8, 9. And similarly from here we're going to come down and then coast along the asymptote. So that was kind of a strange one, but you can see that the graph does cross through the slant asymptote in this section, which can happen, but you can see to the left and the right the graph does abide by the slant asymptote. All right, that's our final graph. Thank you guys for watching, and don't forget to like this video and subscribe to Math with Yosh. Have a great day.